Jay. So, well, I got about 5 after.
Let's start.
Yeah, let's start. Let me just share my screen for a second.
Okay.
I think this is the screen. Anybody see it? You guys see the
Yes.
screen? Yeah, okay. This is just the schedule for the year. Bill Jacobs, I don't think he's on tonight, but a couple of months ago, he volunteered to give a talk on that he's put together on how to do imaging. And one of the things that I think that I think I'm neglecting here is beginners that are just getting into it. And Bill says that his talk is very, very much geared towards that. So next month, I expect that Bill's going to be the main speaker. Then July and August, the Milky Way will start to appear, and I think we can actually take some pictures and compare our results. So that's what I expect in July or August. And the last 3 months are still open. So if anybody's got a topic for September, October, November, just let me know, and we'll fill in those months too. So that's really all I've got. But I guess I'll turn it over to Jerry, and he's going to tell us about asteroids, right?
Yeah, I'm going to need to share my desktop as opposed to a single screen. Is that possible here?
Yeah, that should work just fine.
It's actually showing apps as opposed to the desktop.
Right now?
Yeah.
Okay. Well, why don't you see in Zoom the share screen button?
I'm already in it. That's what I'm saying. When I open that, it's not giving me the option to share a desktop. It's only giving me the option
why don't you drop out of the share screen?
Okay.
And then go back into it.
Okay.
And it'll show you a bunch of things that you can share. And
right.
One of them is the whole desktop.
Okay, I'm not getting that. That's the problem. I'm getting the slideshow or my web pages, but I can't do the desktop.
Weird.
Oh. Yeah, maybe under advanced I can do it. No, usually it has to be allowed to do a desktop. I'll just go ahead and start, and then I'll have to stop and restart when I want to switch to the web pages. Okay. Yeah,
there is a button here I can. Okay, go ahead and do it. And if we have more trouble, we go back and work on this problem.
All right. Well, that's all right. We'll just get started.
Okay.
Okay. Can you see the screen?
Yeah, that's great.
Yeah. It should be a full screen up here. Is my mouse moving around?
Yep.
Okay. All right. So I'll just do a quick introduction for anybody that doesn't know me, which I don't think there is, but we'll see anyway. My name's Jerry Hilburn. I've been a member of the club since 2003. I started the AISIG group in 2003, ran it for 10 years, turned it over to Dave Wood. He ran it for a long time and turned it over to Scott. Back then, I used to do a lot of pretty imaging work, and I liked it and enjoyed it for quite a number of years. We had a lot of fun, but we were working with old antiquated equipment in Photoshop. So the quality of the work that's being produced today is incredible relative to what we did back then. And I'm a fan of all the stuff that gets posted on Facebook. I have an observatory at the very top of the hill at TDS, and I'm talking to you right now from there. And I have moved back to San Diego and am living in Boulevard full time. And the reason for that is so that I could get heavily involved in planetary defense operations with NASA. There is quite an interface available for those of us who like to do astrometric reporting on asteroids and photometry for rotation. And we're going to talk about those things a little bit tonight. The first thing I want to point out is tonight's class is strictly about how to find rocks and is not necessarily a deep dive on the astrometry aspects. Really, we need a separate class for that. The software is different than you need data in order to do it. So we're going to start off by teaching you how to go get data, what data matters, how to determine what the Minor Planet Center and Planetary Defense are looking for each night in terms of follow-up studies. And that's tonight's class. Later down the road, if you guys are interested, I'd be happy to come back and teach the astrometry and MPC reporting. MPC stands for Minor Planet Center, and that is the clearinghouse that takes in all the data that currently from anybody that's reporting, professional or amateur. James, I see you're on there tonight. James is one of a long-term rock hunters from way back. He participated in stuff when we built the very first roboscope out here. Before the replacement telescope was put in by Pat Boyce for Boyce Astro. There used to be a small dome out there, and we ran exoplanet studies for NASA. And when they weren't doing that, I was running asteroid studies. So James, are you there? Was there earlier? Maybe he's not listening now. If you hear me say anything wrong, just chime in. And by the way, as we go along, feel free to ask questions and stop me. I'd love to sort of make this interactive as opposed to just a one-way lecture. So we'll do that tonight. All of these little symbols on the screen here, NASA has a group called the Planetary Defense Coordinator's Office, and they have been well funded now for a few years. When we started doing asteroid submissions to the Minor Planet Center long ago, back in 2005, 2006, there was no planetary defense program. The United States wasn't thinking about being hit by a rock. No place on the planet really cared about the issue in terms of any governmental agencies. And then a few years ago, the United States decided it was time to pay attention to detail, or at least NASA did. And they funded this office, and now this office is operating one satellite, NEOWISE, and is in the process of preparing a mission for DART. I'm going to switch over real quick to, let me see if I can stop sharing. Well, let's see if I Alt-Tab if it'll work. Let's see. Here we go. Can you see that?
Nope, same screen.
Okay, all right, yeah, it's doing that trick. Well, then I'm going to stop sharing. And then share screen, and then we'll go to this one. Okay, can you see it now?
Yep.
All right.
Better.
So all you get to do is go to Google and type Planetary Defense, and the NASA page is going to come up. And what you're going to find here is a long history of everything that's been going on with this new department. They fund this group, and this group uses a portion of its funding to fund the Minor Planet System database and the planetary data system entries for asteroids that are being tracked by anyone that submits worldwide. So worldwide, there are over 600 observatories that are active nightly in one form or another. And of course, it's weather dependent, just like us. We're stuck with weather issues, but there's a steady stream of data that's being brought in through this channel into the Minor Planet Center, which is basically managed by the International Astronomers Union. So NASA funds planetary defense funds the IAU, and all the data that we submit ends up in the planetary data system. And then that data is cleansed, washed, and published at the Center for Near Earth Object Studies. And we'll be talking about this one tonight and the Minor Planet Center. So they have a couple, like I was saying, there's NEOWISE. This is a repurposed, the Wide Field Infrared Survey Explorer operated from 2009 to 2011 and completed its mission. And then NASA gave this to the PDS people, or the PDF people in 2013, who have now begun to use it for studying near Earth objects, near Earth asteroids. And so they built up quite a catalog and some interesting stuff. They are funding the Double Asteroid Redirection Test, the DART mission. This will launch later this year. And then next year in September, close to us, we're going to be able to watch it impact an asteroid and study the results of that impact. The primary purpose of this mission with the impact study is to see if it repositions the asteroid in its orbit ever so slightly. It's not going to make a big difference. It'll be negligible in terms of its path off orbit, but we do want to get a feel for what happens with a certain amount of mass impacting at a particular angle on that asteroid to see if it can be redirected. There's a theory that's being bounced around in the asteroid community that the best way to move an asteroid around with our crude capabilities now is to have a series of very small mass objects that are constantly pummeling an asteroid that might be on a path towards us to change its orbit 1%. And maybe less if we can catch it earlier. But we'll talk about the whole idea of reacquisition and how difficult that is. Because normally in a reacquisition scenario, we may only have 3 months to react.
Is that thing a CubeSat sized satellite?
No, it's
than
bigger. Yeah, it's bigger than that. You can stand next to it. It's a fairly nice sized box.
Okay.
So that's the target is the Didymos 65803. We can look that up. It has been characterized with Arecibo that no longer exists, which is a shame. We have a fairly interesting object look, and it has a moon, which is fascinating. That's what the craft looks like. And I think this is actually a test of one of the panels in its rollout. So in any event, that's one mission. Another mission that's current right now and a bigger deal is OSIRIS-REx. Now, this launched several years ago and recently orbited Bennu, which is a very large asteroid in terms of its comparison to others. Bennu is in Earth orbit, and it has a series of potential impacts about 150 years out that are kind of scary. If it can, but it's early, and you gotta know 150 years from now, predicting it's going to impact us is just a shot in the dark. It's in terms of the reality of it, but knowing that it has a high potential for impact and looking at its size, it's the kind of asteroid that would be an end-of-life event if it were to strike the Earth. And so they've flown a mission out to it. They collected samples off of its surface. In a few years, that sample return is going to bring back material from the planet so that we can better characterize its structure. And we'll talk more about that later. We talked about the Minor Planets Center. This is where you would go to find data that you can download to install in your various star chart software, depending on whatever you have. Most of these databases can be imported. We'll talk more about that in a few minutes. And that's it for that page. So let me stop sharing and let's jump back into the presentation. If I can find it. There we go. Are we back?
Yep, we're back.
Okay, so like I said, class 1, this is all about rock hunting. Class 2 is about characterizing the position in space and reporting these points in space. And we'll report it to the IAU MPC. And then if we decide to have class 3, which is pretty advanced, this is photometry. And what we do here is we actually study the light curve characteristics of asteroids. And the reason we do that is to determine rotation rate. And that's a fairly important thing because a recent revelation about asteroids is as they travel around the sun, and especially those that are in the inner belt, the Yarkovsky effect, the sun causes one side of the asteroid to heat as it's rotating. And then as it turns away from the sun and cools down, that heat yield actually creates a force on the surface of the rock and pushes it out of its orbit. And as it turns out, almost all of our minor planets that are coming around within the Mars to Mercury area of orbit are affected by this. And so we may record information about a particular orbit pattern on this pass for an asteroid, but on its next pass, a couple of things could have happened. One, its orbit is changed due to that effect, and two, its spin rate could be increasing as a result of that as well. It is very common for an asteroid to increase in spin rate until it comes apart. So what will happen to it as it's tumbling, it gets faster, it gets faster, it gets faster, and then boom, it separates. And at that moment when it separates, it creates a lot of rubble and usually a couple of main cores. And those main cores take a completely different path on their orbit. And we're very concerned about that in reacquisition of known targets. We want to know whether or not on the 3 to 5 years that it's been on its orbit and now it's coming back towards Earth, has it broken up? And if it did, is a piece of it headed towards us? So this is a primary objective of photometry, and there is MPC reporting for light curves on asteroids as well. All of that goes into a big mainframe. That data is available to anybody through PDFs after it's been posted. So that's the introduction part of this. Let's talk about asteroid belts for a minute, okay? So here's an Encyclopedia Britannica. There's a throwback image of the solar system. And I think what's important to note is that, here's our what we would call the inner belt area, okay? And there are a bunch of rocks in this inner belt that we worry about. This is where all the NEOs are. The main belt, these are all of the asteroids that are sitting out between Mars and Jupiter in a collection. And though that looks like there's a lot there, in reality, they are very widely spread, but they are fairly stable in their orbits, okay? They have been shepherded for many years by the gravitation of Jupiter and the inner solar system's gravitation working against them. And it is quite rare at this point in our stellar or solar evolution for these rocks to get out of control and fall inwards towards us. Now, as you move out, we get out into the Kuiper belt, and this is an area out by Pluto, and the Kuiper belt is 30 to 50 astronomical units out. And this is a source of a great number of comets that come in. And also the Oort cloud, which begins at 20,000 astronomical units, going out to about a light year, is an even bigger source of comets that come in. There are comets that come in and end up getting caught in Jupiter's orbit, and they will go around many times, burn themselves out, and end up being what we think of as an asteroid at the end of the day, because they're no longer outgassing, all their materials are spent, they're in a stable orbit. Sometimes they get pulled into a position behind Jupiter or into a position in front of Jupiter. We call that area Trojans. That's where the Trojans are at, and they belong to Jupiter. We've learned that there are also Trojans with Saturn. We have not been able to identify them with Uranus. There's not enough time for studies or Neptune, but we believe that they exist out in this area too. It just only makes sense because of the way that gravity works in these stable orbits. There should be followers and leaders. Bennu, in our case, the one we're talking about having done the recent sample for, lives right in front of us. And it has kind of a horseshoe orbit where it'll come around. And sometimes, and that orbit is circular in this manner in front of us. It twists ahead of us. So that's an unusual orbiter, but it does have potential for impact, and it is in Earth's orbit. Any questions on this? Basic introduction, done. Let's talk about some really interesting data. NEOWISE, that satellite that we were talking about that was out there doing infrared studies, when we picked it up, they started repurposing it to look at what's flying around in our local solar system. So that blue ring on the very outside, that is Mars, and the light blue is Earth, and then you have Venus and you have Mercury. All of the gray stuff, that's the asteroid belt. And you can see it extends between Mars and Jupiter. These are real detections by that satellite of all of the gray mass, all of that stuff are the asteroid belt itself. And it does get pretty darn close to the orbit of Mars, but it doesn't rarely does anything fall out of that and come inward. But around the light blue circle, you see all these green dots. These are actually near Earth asteroids of 100 meters or larger. And included in these green dots are 1,100 asteroids that are a kilometer in size. Okay. Now, a kilometer size asteroid is an LE asteroid. That means if it hits the Earth, it will end all life on the surface of the planet. Every 50,000 years, a rock about that size has found its way to our surface in one form or another. But by the time it gets here, it breaks up usually because of gravitation. And there's only been one event that was significant in the last 250,000 years. Prior to that, some stuff went down that wasn't so cool, but we weren't around to worry about that. The yellow ones are comets. So those, you can see they're all escaping pretty quickly. We're only looking for 4 years. We had a really interesting period in 2000, 2010 when there were a lot of inbound comets, more so than outbound. And so this is really reflecting the outbound nature of that period of a dense comet period. And now it's kind of calmed down. We don't have as many comets inbound. And so this continues. This is actually 8 full, this is not the entire one, but you can see 2014 to 15 to 16 down on the bottom here. This is continuing in terms of its studies, and the number of rocks continues to increase significantly. Any questions about that one?
Sure looks like a lot of rocks.
It is. And though this looks really dense, it's still, these rocks are still far spread from one another, right?
Sure.
Yeah.
Yeah.
So there's that. Okay. So as far as the distribution of asteroids that we are aware of in terms of their size versus the number that exists, the largest one that we know of is Ceres, and then there's Vesta and Pallas, and there's some rocks that are further out, Haumea and Makemake. These are new minor planets that have been discovered outside of, there's several actually. We even flew by one with the New Horizons spacecraft secondary mission after it flew past Pluto, but that was a small potato-like rock. So like a lot like Tautatis. If you look at Tautatis, you're going to see that it looks like a potato too. It's got 2 lobes and it's separated out in a strange configuration. But big rocks are not, there's just not that many of them. Around 100 or so are greater than 200 kilometers in size. Around 1,100, and this number has changed a bit, but around 1,100 are greater than 100 kilometers. And then 50 kilometers, the number begins to go up. We have around 1,000, and then greater than 30 kilometers, 10,000, and so on. And then when you get all the way down to the little bitty rocks, the ones that are more common that we look for as near Earth asteroids, there are over 1 million that are out there at this stage estimated, with a little more than 70% of those having been captured at some point. In terms of rocks that we actually understand the orbital characteristics of as near-Earth objects, we're looking at about 25,000 right now. And that number should be about 10 times that size. So we're right at the beginning of discovery. There's still opportunity to find things. However, most of that stuff is being found in the sky surveys that are going on. There are these 8 projects that do nothing but do continuous nightly wide field photography, and then they store that and make it available to amateur public scientists. Anybody can do this. Kids do it, You can get involved. The Planetary Defense page has information on how you can go to this one site and they will give you access to different photography, and then you sit there and you look through it to try and identify little asteroids, right? So that's going on. The people that I work with, the 600 or so observatories that are doing this type of work, really don't have a focus on discovery. That's not the interest. The interest is really on reacquisition and capturing a lot of data during the 3 days to 3 weeks that we will have to capture data. And we're going to look at why that is here in just a minute. Let's see, do I have anything I want to show here? Let me move this out of the way. Okay. Oh yeah, there's a little blurb here. Currently, NEOs that are 140 meters and larger in size than a small football stadium, these objects represent a risk to a population zone as opposed to a risk to the entire Earth. And so far, about half of those have been discovered as NEOs. So these are objects that are big enough to create havoc. And when we talk about havoc, what we're talking about with one of these rocks is, if it were to strike LA, it would rain rocks in San Diego and all the way up the coast to San Jose and out, and it would create a crater in the ground about a mile wide and probably 500 to 1,000 feet deep, depending upon whether it was metal, carbonaceous rock mixed with ice, or some sort of a silicate rock mixed with ice. As it comes in, if it makes it to the ground, a rock that size would also create a fireball that would set things on fire in San Diego. It would burn trees, it would burn anything that was outside. The blast would arrive about 3 minutes after the impact with 300-mile-an-hour winds. So if that strikes the ground, something that size, that's a pretty good whack. We just had one of those back in the 1900s, the Tunguska event, out in the middle of the Russian wilderness, that knocked down 25,000 square miles of trees and created a lake. And at the bottom of the lake, the rock is still sitting there, the remnants of it. That was a fairly interesting event. Now, about every 100 to 150 years, we're supposed to have an event like that. We're due. It's time. I can think of a few cities I want to take out, but that I digress. Next. So let's talk about how near-Earth asteroid orbital groups are identified. So everything that's happening near Earth between Mars and Mercury, there's 4 classes, and it has to do with the semi-major axis of each rock's orbit. Those that are approaching us but are exterior to our orbit, their semi-major axis is larger than Earth's orbit. These are called amours, or amour. I can't pronounce it right. So amours is what I call it. Apollos are Earth-crossing near-Earth asteroids, and they have a semi-major axis larger than Earth. And you can see that second one, how that orbit kind of crosses us and then goes outside of us. And a lot of times this will go all the way out and even go around Mars. So it'll be on the outside of that. And it threatens both of us. It threatens Earth and it threatens Mars. And it could be, and it is likely, that given the shape and deformation of Mars, it was struck by a fairly large asteroid at some point. I'm not going to say that it took out the atmosphere. We don't know those things, but what we do know that there is a very heavily deformed, misshapen part of Mars, and it had to be from some type of an impact. And the guess is it was probably a fairly large Apollo. A10s, Earth-crossing NEAs with a semi-major axis smaller than the Earth. You can see that the orbit's tinier, the major axis is flatter. These are named after an asteroid called Aten 2062. Now, the funny thing about these numbers is The lower the number, the older the discovery. And these are numbered and named rocks, and they have families or groups that we can identify. And then finally, the Atiras, you can see this is a fairly high number. These guys have only recently been discovered. They're much smaller, and they orbit between the Earth and the Sun. They threaten Mercury and Venus, and they could threaten us in time because of the Yarkovsky effect and because solar winds push rocks around as well. So
Jerry,
there's that.
Jerry,
Go ahead.
Do those numbers go all the way down to 1? So that there's
Yeah, Ceres was
more.
the first one we ever found.
So there's at least 1221, 12,021 AMOR objects, and obviously.
Oh, I don't know
more
if
than
it
that.
counts that way. What these are is the order of how they were found. That these are numbered as they're found.
Okay.
These just happen to be named after that particular. That was the first asteroid where they noticed this type of an orbit and said, "Aha, we're going to give this a name because there's a bunch of them that do this." And so, there was all kinds of trouble trying to figure out how to name asteroids for years. And now it's finally settled down into 3 classes. There's stuff that's way out there. There's the main body, the main belt, and then there's the inner solar system, the inner belt. And they've stopped relying. If we start talking about families and groups, there's 100 of them. Vesta's got a group, and it's from an impact that happened to Vesta, and there's a bunch of little rocks from that impact that are all Vestoids, right? Anyway, that's the grouping. So the NEAs are the ones we really care about. This is the one that would be really interesting to us. All right. So let's stop and talk about the next step here is great. We know where stuff's at. We got rocks way out in the Kuiper Belt. Good luck finding anything with your telescope. That's just about impossible because that stuff runs about magnitude 20 to magnitude 28. It's just, forget it. It's even hard for ground-based 200-inch telescopes to look for that stuff, right? So the satellite or the space-based telescopes, they have a little bit better time, but they're not very good at it either. You've got to get out there with the telescope in order to find stuff. So that's part of the problem. It's very faint to begin with, so we don't even bother with Kuiper Belt. Main belt, that's really easy to find asteroids in because 1, there's a lot of them, and 2, they're in every star chart tool you can think of, and 3, they're a lot of fun to take and make pictures of. So that's something you can do, and I'm going to give you an example of that right now. Let me stop sharing, and I'll show you something that is fairly classic. We go over here. Where is this? I think it's this guy here. Let's go there. And then somewhere out here, that's Florence, okay? 3122 flyby, right? Now, this is actually not a main belt, but it's nice because I did this with Mike Chasen, and we had a lot of fun doing it together. So here's what an asteroid looks like. It's nice and bright. I think we were actually at like magnitude 9 on this the night that we took it. Can you all see that little bitty dot moving by? Is that visible?
Yeah.
Yeah.
Okay. So it's running again. So we used Mike Chasen's observatory, and he had a refractor in there. And this is a bright asteroid. And this one was close. So it's not actually considered it's a near Earth object, but it's not one that Earth crosses. It's outside. It's more of the Mars area that it orbits. So that's kind of fun. And when you start looking at your star charts, stop it. All right. Let me go back to, let's see if I can do this. Stop sharing. And screen share. We'll go back to this one here. Okay, so if you've never gone out and imaged asteroids before, you want to start with the main belt. And the reason you do is that there's just a ton of great objects out there. They're visible every night. No matter where the Earth is in its rotation, there's going to always be 90 to 150 less than 15th magnitude objects. If you've got a ZWO camera and a refractor or even an SCT, you're not going to have a problem capturing information. Now, is that information worthy of submission to the NPC? They don't even want to hear about it. That's not the kind of stuff they're looking for you to submit. But if you haven't done this before, it's an exercise to go out and figure out how to get the pictures, bring them down, process them, put them into a movie. It's even an exercise just to see if you got it when you first set up. Did you really nail it? And there's been night after night when I've helped a lot of people that are trying to learn this. We'll go look for a main belt object. They'll get the data off of their star chart system, and then we'll go to image it, and it's not there. And we're going, well, what's that all about? And it turns out that like Starry Night Pro and some of these other tools that are out there have a library, but that library doesn't get updated unless you actively go and push a button to get that data to be pulled in. So there's a little bit of a learning curve, but the main belt objects are the perfect place to begin. They're bright, they're everywhere, and they're on the ecliptic. You face south, you pretty much can assure that any night that's clear and you want to do a movie and take like an hour's worth of samples, you can do that. So I recommend, as the first step, shoot main belt objects and get some of those under your belt before you attempt to work with NEOs. Now, if you don't have a decent ability to import information like astrodat.db, we'll talk about that in a few minutes, or your software like Sky Tools has a button on it that will let you update the latest information from the Minor Planet Center. And so those of you that use that, it's easy to go find asteroids to hunt tonight in the main belt. I know that the Sky does it. There are other tools. Go ahead. Comments? No? Okay. So I know that other tools do it, but the freshest data, the data that is up to date as of yesterday, is at the Minor Planet Center location under data, and you can download information in hundreds of ways through that system. So we can, if after this you want to try and do this and you need help, I'm happy to coach. We can do a Zoom session from wherever your location is, and I'll step in and help you find stuff for the night, show you how to hunt it down and have some fun with it. If you have any of the tools that are listed up here, except for Sky Live, the Sky Tools, Stellarium, Search the Soul, Starry Night will all pull in Asteroid, ASTROB data set, which is everything that the Minor Planet System has or Center has published since yesterday. So that's an easy way to bring the catalog in to your star chart system. Now, as an example of what that's all about, I'm going to stop for a minute here and switch back to another screen. Let's see. I think this might be the one. Yeah, let's go here. Okay. So I like, for demonstration purposes, I like to show off the Sky Live, because one of the nice things about the Sky Live is you can load this up. It's easy to get your location into it. It will figure out what time. It usually starts you after, it starts the evening after it's gotten dark for its display. And it has a nice list of NEOs and asteroids and comets that are available right now to go and look at. We'll look at that in just a minute. I went through and I did a hunt for an asteroid that we could talk about. This one here, 2021 KM1, that is available tonight. In fact, it is passing right now tonight. And this is TDS. This is our location. Can y'all see that little yellow circle there?
Yeah.
Okay, watch this. First thing I can do is I can play with the hour. So I know that at 4 o'clock or 5 o'clock this afternoon, it was rising right around 4 o'clock. That was its position. And it's off to the north and it's circumpolar. So it orbits in a position that is around the pole. And as I raise the hour up, you can see that it's rising. And we're not actually seeing its motion yet. We would have to actually dive in on it deep, and then a track would develop. You would see it over the hours. So just knowing where it's at's the first step. Once you get that, get your telescope on it, fire it up, then you've got something to shoot. And the nice thing about this one is right now, tonight, it's at around 13th magnitude. Oh no, it says 20th, but that's not correct. I think that's absolute magnitude. I was looking at it earlier on one of NASA's charts, and I believe it was going to come in a lot brighter than that. In any event, that's 7 o'clock, 8 o'clock, 9 o'clock, and notice what it's doing as we go through the night. It's coming back down, and by morning, and let me go back up a little bit here. There you go. By morning, it's going to go down, and then tomorrow night it'll go around and around and around, and so. But it's going to get dimmer and dimmer each night because it's actually moving away from us in a spiral. But this is how you use a start. Go ahead.
Jerry, is it spinning? What's the rotation rate?
I don't know. I just looked this up as a demonstration of, they all spin, by the way. Yeah, it's spinning. Yeah. I don't know its exact rotation rate, but this can be accessed at the Minor Planet Center photometry database. They can give you past photometry if it exists, and you can use that to determine spin rates.
Right, so you could, in addition to just tracking the thing and taking an image sequence, you could actually do photometry on it and see generate a light curve.
Yeah, it'll generate a light curve, and also its position is important. You can submit that to the Minor Planet Center for astrometry. So that's kind of interesting. That's how I use star charts to get a feel for whether or not it's worthwhile to shoot a target on a given night. Which brings us to a discussion about entry points for that. So let me see. I want to go see if this next, the next slide is exactly about that. All right, I'm not going to show the slide. I'm just going to stay with what we're doing. Let me get back on there. Okay, so there's a slide that talks about the next several pages that I want to get into. So let's say that now you want to go after an NEO, okay? And not a main belt asteroid. Remember, those are going to be along the south. They're everywhere. You can't miss them. Like, for instance, if I click on asteroids here, there's Vesta. Where's Vesta? Let's go look. It's planetarium. And that throws us over here. And as I zoom out, is that even visible tonight? I don't know. Let's see. Yeah, it might be. It might be visible. And we can get on the clock over here. Let's see here, J2000, 15 deck. Yeah, that's visible tonight. And it's a magnitude 7. So that's well worth shooting. And hey, look, there's Leo, right? So Vesta's right up there in Leo right now. Sounds like fun, easy to shoot. If you take about an hour's worth, you're going to get a little line. A motion will come out of it. That can be interesting. Here's one that I shot just a few weeks ago with a group out of India and that I work with in an observatory in India. And this is Apophis. Remember about 12 weeks ago when we had Apophis come by? So this is 30 minutes. And look how far that moved in 30 minutes. In fact, we could only get data for one night off of that. From here, it would have risen and then set within 3 hours. And that would have been the only astrometric data that we could collect here in our time. They were able to get more data than we would have ever gotten here, and it would have been too low. And this is an Earth killer. So it's a pretty important rock in the list. But the way that it orbits, it comes from the south, goes up, and then down around the Earth, and it does that last portion of its minor axis in less than a day. And it's moving fast. So anyway, back to Jerry,
finding
stuff.
Jerry, one question. Is speed, as far as information, also included, or is that just a guess on
Oh,
PowerPoint.
no, we know the speeds of all of them for the most part. It's easy to calculate. Typically stuff, all right, so when we say speed, we're always doing that relative to Earth's position. So if I say something's approaching us at 17 kilometers a second, which is pretty, anywhere from 7 to 17 kilometers a second is typical for an asteroid. Now, most of them are approaching us from behind us in terms of our orbit, right? The majority of them go around the sun the same way we do. But some of them follow us and they orbit us. And Apophis is one of those that orbits us. And its speed as it approaches its minor axis is around, I think, 14 kilometers a second, right? So that speed is relative to our position. There are multiple types of speed that can be measured, right? Speed in its direction around the sun as it orbits us, speed as it orbits us coming in at us. You really, you have to make it relative to something in order to quantify its rate of motion. Does that make sense?
Yes, it does.
Okay.
Got it. Thanks.
All right. So my favorite place to start when I'm looking for something is the asteroid and comet connection, Hohmann transfer. This has been around the entire time that I've been doing this, since 2004. And they keep this thing up. The fun part is Earth's busy neighborhood. We'll talk about that. This is just a direct link right into IMPACT, the Minor Planet Circulars. Okay, circulars. These are publications of all of the observatories that have reported, usually in 4 to 6 hour increments. And these are updated constantly, 3 to 4 times a day, okay? So the Minor Planet is taking information in and then turning it around and pushing it back out 3 to 4 times a day. However, if you go to Minor Planet Center and you open up their stuff, it's terse, and you really got to have an eye for what it's reporting. But this redoes that in a nice format, day by day. So here's Thursday. Here's what the rocks identifications that have been reported, or the circular. And then as you go down, this circular reported on 2021 KN1. It says a lot about what's going on with it. Information here was picked up at a certain universal time by Mount Lemmon, was observed May 20th. I'm sorry, May 25th to the 27th, was confirmed by Pan-STARRS, yada, yada, yada. And if you really want to know more about it, then these links will take you to more data, okay? But that's not the best one. The best one is to come here and just go to the traffic report. So if you click on traffic report, you get this listing. And I love this listing because it's broken down and much simpler to understand. Earth's busy neighborhood. Okay, so this one is objects that are currently less than 10 lunar distances from Earth. So April 2nd, May 11th, May 18th, May 19th, May 22nd. These are the dates that it reaches closest approach, and it would be brightest. And this is their size. And this is the object's identifier here. And inside 10 lunar diameters from the 21st to the 27th. Who discovered it, when it was discovered. Okay, so this is 2021. So that's the year, and that's an incremental designator for it. And if you're seeing that, that means that this is the first time it's been discovered. It's 42 meters in size. It's about 8.37 lunar diameters away from us. Looks like it was at 62 lunar diameters May 1st when it was discovered. And on May 24th, it approaches it. So we have basically 23 days to determine whether or not that's going to strike us. And that's a 42 meter object. So that's something that's pretty small, probably would break up and burn up on the way into the atmosphere, unless it was a chunk of iron. If it's a chunk of iron, it's going to make it to the ground. It'll take out a neighborhood, a small town. That's what that would do. So there's more information. This is what makes everything just lovely. I can press the button under to the right, go to the Minor Planet Center and get information. I can go to NEODIS, which is another type of a lookup, and that's going to tell me everything I ever wanted to know about its history up to today. I can get an ephemeris for it so that I can look at its actual, hey, when is it going to arrive? In 15-minute increments, what is the right ascension declination? I can go to JPL and I can look at its orbit. And so I did that for an object. We're going to start with one right here. I went and looked at this 2016 AJ193, and I believe that that's one that's arriving in August, and I picked that one in August because it's a 676 meter wide rock, and it'll be coming in August. From August 20th to the 22nd, it's going to be bright enough for us to see it. This is a return visit, obviously, because we saw it in 2016, and 5 years later, which is pretty typical, it returns. Okay. Now, there's no indication yet that it has a reacquisition. So this may be one that we can't see right now, but we know it's supposed to return. And if it's returning and we don't see it right now, we want to start looking for it as early as late June, early July. And we can look at its past orbit. Because of its size, it probably hasn't moved much off of that orbit, okay? So what does that look like when we go to this JPL small body database browser in terms of its orbit? This is one of my favorite tools. This will plot 1 day at a time, or whatever increment we want to look at it, its position relative to Earth. So Earth, that's us right there in Earth, and that's its current position there. And we can look at it this way. Which direction is it approaching from on the plane, right? It's coming from underneath. Or is it going to do anybody in San Diego any good right now to look down there for that rock? What's your guess? Think about standing outside, looking up at the middle at midnight, into the sky, down to the southern horizon. What are the chances that that thing is visible right now?
Probably too far south, isn't it?
Yeah, right. That's why we like those new observatories they're building down there in Atacama that are going to do this type of study in real time, right? Okay, but even with that being said, what I can do is kind of imagine, look at our position relative to that. If it's sunset, are we going to be able to see it at sunset based on where Earth is right now? Probably not. But as the Earth turns towards morning, we might have a shot at seeing it, because you got to remember, it's not always visible, you know, in a southern area for the full night. Anyhow, moving on, let's run it forward a little bit. We'll step it forward 1 day at a time. And down here, we can see the Earth distance, we can see the sun's distance, and we can see the date that we're looking at, 5/28 right here. So I'm just going to go ahead and step, and we can see everything moving now, right? Earth is coming around. AJ193 is coming around. Now we're into July. Okay, now in July, what are the chances we can see it? There's a shot. We'll have to go look at the ephemeris for it, but there's a shot that it's visible. And of course, it'll be down to the south. And we'll just keep watching that and move that up. And now, has it reached the plane? It's visible now, right? That is going to be visible.
That plane's the ecliptic plane, right?
Yeah, that's the
It's just breaking.
Right there. Yeah, it's just breaking it right there. That's definitely going to be visible at the midnight sky. No question about it. And that's by August 13th. And we may see it a little earlier than that. So when I'm making a calendar of rocks that I want to study, I take a full 2 weeks prior to when I think it's going to be visible, and I go get the ephemeris for it so that I can find out whether or not it makes any sense for me to schedule observation time on that rock, right? I don't know if I'm going to acquire it. I do want to acquire it. The earlier, the better, but that's why we call it rock hunting, okay? There's a reason I named my observatory Catfish Software or Catfish Observatory, because I like to fish. And this is fishing, if you ask me. We just don't know when that rock's going to show up. We have a pretty good idea looking at the orbital diagram when we can start to think about it showing up. And when we get into that mode, the next step is to generate this. How many of you are familiar with what this is? Anybody? James, are you still there? All right, I give up. You go to NASA and this Horizons interface, Solar System Dynamics interface, and I'm going to put all the links in an email, or not an email, but into the club's group so that you can go check this out for yourself. But in any event, you can open this interface up and generate this ephemeris for any object in the solar system. Okay, and the trick is you come up here and you're going to pick the name that you want for whatever it is you're studying. You can change that. And then change the time span. So you open this up and it lets you set a time span. I know that somewhere between the 19th and the 22nd, this thing is going to approach the closest location and brightest point that I can see it at. I can set step sizes in minutes, or I can set them in hours. Some of these, you want to set them in 1 minute increments because they move so fast and you want to get in front of it, you know? So that's what it is. When you click on use specified times and hit generate the ephemeris, there it is. And what you get here is the date, the UTC time, the right ascension, the declination, and the apparent magnitude. That's not absolute, that's apparent from Earth. So this is a great rock because it's going to be visible at 13.6 magnitudes, just about any optical train that exists out there, okay? Then around the 21st, it starts dimming. It gets to 15th magnitude. And pretty quick, within a few days, it's into the magnitude of longer focal length telescopes, that the smaller ones are not going to catch it anymore, okay? So this is an important tool because it is reporting information and updating constantly. It pulls data from the Minor Planet Center. A lot of this is historical, but as the object closes and people begin to report on it, all of this will change. So what I'm showing you today in terms of right ascension and declination for the object location and its apparent magnitude is definitely going to change by August. That's why before you do a night's observation run, you need to go run one of these for whatever it is you plan to shoot, because you can be sorely disappointed by something that's supposed to be bright and moving fast and thinking that, well, I looked it up 3 days ago and the data was there then, and then come back and find out it's been updated in the last 12 hours and it's all changed. That is a great tool for that purpose. So that's the trick. You start at ACC, you go look at the traffic and find something you want to look at, plan ahead. You need to know something about how your limited magnitude. There's a trick for that. Let me show you this. Oh, I take that back. There is no trick for that. We need to talk about your limiting magnitudes. How many of you actually know your limiting magnitude for your optical train? What you got, Carter? How faint can you go? How low can you go?
At most, well, my limiting magnitude so far that I've tested is to 15 with a good long exposure. I haven't tested, I'm going to test 17 here soon, but 15 has been pretty good.
Okay, and what type of equipment are you running?
550 millimeter refractor, 100 millimeter diameter.
Okay. Now, do you know what the arc seconds per pixel are for your camera setup?
1.76.
Okay. So you can make movies and you can have a lot of fun with this, but you cannot submit that data to the MPC because the requirement for the MPC is 1 arc second or less per pixel, right? So that's the challenge, is finding where is the sweet spot? Can I make movies and have fun with it? Absolutely. Can I see a lot of motion? Yeah, absolutely. 15th magnitude gets you in a pretty good place. But unfortunately, the pixel size is an issue. You need to be beneath that. Who else knows their limiting magnitude for their equipment? Let's share.
Well,
Come on, all you PixInsight users. Somebody out there must know it.
The limiting magnitude depends on exposure time.
Yeah.
So, what you're asking is what's the limiting magnitude versus exposure time, right?
Excellent question, because I want to run into the next part of this. When you actually go to test that, the maximum amount of time you ever want to take an exposure for asteroids is 1 minute. You're going to do 10 seconds. What I recommend is you find an asteroid that's on the edge of what you think the faintest you can get is. Better yet, forget the asteroid. Go find an open cluster, okay? And look it up on a star chart and find out if you've got, what the range is of stars in that open cluster. AAVSO has a bunch of samples for that, or they have the calibration samples. Just look up their calibration targets and run an image at 10 seconds, 15 seconds, 30 seconds, 45 seconds, and 60 seconds. You can't go longer than a minute. Doesn't do you a bit of good to go longer than a minute, because by then your asteroid, especially NEOs, are going to turn into Tic Tacs, and they'll smear across your pixels, right? All right. So the next thing you got to know is, when you're doing the asteroid, is how fast is it moving? How many arc seconds is it going to cover in a minute, right? If it's going to cover 5 arc seconds in a minute, that's 60 seconds divided by 5. What should my exposure time be to keep it on a single pixel?
60 over 5.
Yeah, it's 12 seconds. So the other thing that happens with really, really, really faint stuff between 18 and 21st magnitude is that if it's moving fast like that and you're trying to get a 12-second exposure with larger optics, that might work out, but it can also integrate itself out of the picture. That is a misery, and it's hard to explain, but it happens. So there's an art in calculating the length of your exposure relative to the motion of the object and its magnitude. And it all begins with doing a series of open cluster runs to determine how faint can you go in the shortest period possible, right? That's the game. So you got to do all that pre-work. You got to do calibration workup before you ever even think about shooting an NEO. And the first step is go learn your limiting magnitude. The second thing is go calculate what your arc seconds per pixel are. Now I use a website for that. Let me share that screen for that one. Let's see where that bad boy is. I think it's on this one here. Yeah. Astronomy Tools CCD calculator. This is a very useful tool for determining what your resolution is going to be in arc seconds per pixel. You put in your CCD pixel size, which I have a 1600 mm cool, old beast. I don't care about the lobe noise or glow. My telescope's 3250 millimeters, and so my arc seconds per pixel is 0.24. Now, this is particularly handy because I can actually get away with bending 2x2. But if we're talking about something more in the size of a Meade 10-inch at 1600 millimeters using that same setup, now I'm down to a half arc second per pixel. That's good. That's not bad at all. And I can see that with that particular camera, if I go to 800 millimeters, I'm in a real nice sweet spot. Almost 1 arc second.
So Jerry, does for these dim guys that you can't make the limiting magnitude on while it's on a single pixel, does anybody tracking these babies?
Oh yeah, I only have a 16-inch mirror. If you can use if we come down to the lip and use that 22-inch mirror and slap a camera on it, it's going to do better than what I'm doing. That's another, what is that? 6 more inches of mirror. So the larger the telescope, or the longer the focal length, and the better the chance.
The better.
Does it make-
What I'm asking is, instead of tracking the sky, we know the direction and speed of these guys. Are people tracking the asteroid itself, even though it's below the limiting magnitude of your scope?
So it is
in order to get to
possible.
long integration times.
It is possible to track on the object itself, okay? And you'll get these lines from that flowing by. They look like, a star trail. And the object is moving through space, and you're on that object, and the star trails are going by like this, right? So that's
Right.
one way of doing it.
Yeah.
Another way of doing it is to stop the motion of your telescope in the location that the asteroid's at, and look for lines that develop that are counter to the circular motion of the stars. If you just put a camera on the ground and shoot at the stars with no kind of motion at all, you're going to get these star trails. Well, it's possible to detect asteroids that way because they won't move with the star, right?
Right.
They have odd angles. Not all of them, but for the most part, the 99% of them. So that's another technique. And then the other technique is just to have it walk through the image, right? So I do a lot of walk through the image, and I don't do I don't have the ability built into my scope. I have an older version of Losmandy 1.1, and I don't have the tool that would allow me to adjust my tracking rate in right ascension and declination dynamically. Okay.
Got it. Yeah.
And there is software for that on the more advanced and newer mount systems. I have a very old MI250, and which is perfectly fine for what I do, but doesn't do all 3 of the tricks, so to speak. Right.
Yeah.
Okay. Anyway, let's get back to where are we at. Okay, let me share screen. We'll go back to here. So finding NEAs. Another trick is to go to CNEOS, and I love this. Let me open that up if it'll work. These are all related to CNEOS. I just showed you home and transfer, the traffic report. And it's basically a rabbit hole. You go to this first page, and then you find something you want to look at, and then over to the right, you have all the links into the other places except for CNEOS. And let me see if we can open that. Bingo, there it goes. Now let me switch to that. All right, Center for Near Earth Object Studies. If you start at the home page, you get top stories. They try to update this, but it's not all that, often that they do. The last time here, we're looking in March for Apophis. And then what's here are really interesting rabbit holes that take you to things like a tool to look up near Earth objects. Well, that's what we were just on, the body database browser. That's hard. What I really want to do is I want to know, what are the close approaches to Earth coming up? So we go to NEOs, and here we have NEO Earth close approaches, and I can say near future within 60 days, and I can say any distance, because basically we're talking out to, let's say, 0.2 astronomical units, and no limit on the mag. I don't care what the magnitude is. I just want to see them all. And then I can just dump them straight to Excel, okay? I don't have to stay here in this interface trying to use this thing. Or option B, I can do them 100 at a time. And then the fun part is to sort them by their magnitude, if it'll let me here. There we go. And now I know that if my limiting magnitude is around 20, which mine is 20.7. So if I come down here, everything above this line is potentially worth taking a look at. And keep in mind that this magnitude that's calling it out doesn't necessarily mean that that's what it'll actually be when it gets here. That's just what's anticipated. Then over here, we have the date of the close approach. And remember, this was in the next 60 days. And then once I see something worth looking at, I think, wow, that's 17th magnitude. That might be in the wheelhouse. And it's a 1.1 kilometer rock to 2.4 kilometer rock. That's pretty cool. I like that. It's not going to get super close. It's 73 lunar distances away. Let's go look at it. So we open that up, and now we're back to the browser. And here I can hit the orbit diagram, and we're back to this tool, which is kind of cool, right? We can hit back on that, and we can then go, hey, make me an ephemeris, okay? And then you do it for the dates, and I have that set for the wrong dates, but we'll go ahead and generate it. And now I have right ascension declinations and, aha, apparent magnitude, okay, is 16. So why does this show apparent magnitude and this show HMAG? Because HMAG is known as the absolute magnitude. Who knows what absolute magnitude is?
It's usually the magnitude at 1 parsec or 10 parsecs.
I think that's correct. 10 parsecs from the sun.
Yeah.
And yeah, so that's a long way out. Parsec is like what? I forget how many astronomical units, but it's a grunch. And we don't really want to look at it at H magnitude, but if we can see this and go, oh, wow, you know, maybe something as far down as 24.9 might work. Let's go look and then run an ephemeris and generate it. And now we see that its apparent magnitude is 22. But then again, the date that I set is not the right date for that. That's out in August, right? It may have already passed by that point, remember? So I would have to change this date. Let's say that we did it for June, delete, set that to 6, and we'll go set that to 6. Or no, let's set that to 9. Give it 3 days worth of numbers, use those times and generate it. And now its apparent magnitude from Earth is going to be, well, it's closing, but it's still 22. 22,604, 597, 58. It's getting brighter. At some point, it's going to get really bright. And that will have to do with the date that it's supposed to arrive, 28th of June. Let's go just one more time for fun. And we'll change this to the 28th of June. And we'll use those times and we'll generate an ephemeris. And 22. Now that's a lot of, let me get over here and drag it down. Ha, no good, no go, bad call. It goes to 23. So it's never really going to get bright enough.
So it's too dim for your setup, right?
Even for me, correct.
Yeah.
I can't play ball here. Palomar could do this all day long, right? Ken, what's the limiting magnitude for Palomar scope? Do you know?
Well, they don't specify it this way. It's probably magnitude 22.
Okay.
But I don't know how they're calculating it. You know, in terms of exposure time or exactly what they're doing.
Right. Everything we look at here when they put these magnitudes in, we're looking at the ephemeris is based on, you know, apparent magnitude that is photometry based from Earth and in its distance. And if we could dig into it, but it's not going to vary that much from scope to scope in terms of the camera. You may see a difference in 0.1 to 0.3, something like that. But your setup is about a minute long. That's as much as you want to take the length of time you want to do on an NEO. Now, the other part of this, which is kind of fun, is impact risk. And if we go here and go to the Century database, everything on here has a pretty good shot at hitting us at some point in the future. And the year ranges are out here. So let's look at Bennu. We just sent a craft out there to look at that. There it is. Discovered in 1999. Looks like we get a chance to get hit in 2175. Look at this one. Distance from Earth, 0.17. And that is minimum distance on the target plane to geocentered measured in Earth radii. So that's less than an Earth's distance. Okay.
Go look at 2181.
Oh yeah, there you go. Now, NASA doesn't point that out. It's long into the future, right? And there's no reason to get people upset. But somebody inside the government said, thinks we best go send a spacecraft out there and figure out what the material composition of this rock is, because this bad boy could be trouble, right? Now, if we want to look at this, oh man, energy, 1.2 E plus 3 megatons. V impact at 12 kilometers a second. Diameter is 0.490 kilometers, 490 meters. Mass is big. So there is a way to take this information and have a little fun. And that is, let's see, impact. Yeah, that one right there. God knows I've been there a dozen times at least. So we go over to this nice little fun thing, Impact Earth. And the impact effects program, there is a trick here. Let's see here, calculates. All right, there we go. So if you're standing, this is fun. Okay. How far y'all want to be away from the impact? In kilometers or miles?
200.
200 miles. Okay. Let's see what happens at 200 miles. And the projectile diameter looks like about 460 meters, right? It was 0.460, something like that. Let's go look. It is 0.49. Okay, so 490 meters wide. And the density in kilograms given by, that's going to be updated when the materials come back. Okay. Let's see here. Ooh. Let's just choose a density from the list. We think that this is a somewhat dense rock, but not iron. Okay. And we know that the velocity relative to Earth is 12.68 kilometers a second. Okay, and the impact angle, almost nothing comes in at 90 degrees. For something to hit us at 90 degrees coming in, it would have to be almost dead on our orbit. So nothing comes in at 90 degrees. Most stuff we're going to calculate at 45 degrees, just because that's kind of a centroid area, but you can play around with this and see how much worse it gets as you change its angle. And yeah, exactly.
Sorry,
and
yeah.
We'll slam this into sedimentary rock, okay? So out in the desert. And what does the effect say? Well, here's how much energy is there, 3.55 times 10 to the third megatons of TNT. The average interval between impacts this size is about, not very often, 1.3 times 10 to the fifth years. Major global changes. The Earth is not strongly disturbed by the impact and loses negligible mass. That means a sum of our mass is going to go up into space. It does not really change our tilt, 0.05 of a degree. It does not shift our orbit noticeably, so it'll be fairly minor because we're big and small. It breaks up at about 162,000 feet, reaches the ground in broken condition. The projectile strikes the surface at 12.4 kilometers per second, or 7.73 miles per second. Wow. It produces a whole lot of energy. Crater shape is normal. Transient crater depth is 5.29 kilometers, 3 miles deep, 1.6 miles wide. The final crater after the impact is about 4 miles wide. Final crater depth is 1,700 feet. It creates a complex crater because it's multiple pieces. Half the melt remains in the crater where it's average. Thermal radiation. At this impact, little vaporization occurs, no fireball is created, therefore there's no thermal radiation damage. Remember, we're 200 miles away. A minute after the impact, we'll have a 7.0 earthquake, and that'll last a while. And the intensity is at a distance, let's see, felt indoors by many, outdoors by few during the day. At night, some people awaken, dishes, doors rattled, not as bad as we would think at 200 miles. The ejecta will arrive 4 minutes after the impact. So where we're at 200 miles away, 4 minutes, some of the ejecta will arrive. A fine dusting of ejecta with occasional larger fragments. The thickness the mean fragment diameter is 1.86 millimeters, so volcanic in a sense. The air blast comes 16 minutes later. It's less than a PSI. By the time it reaches us, it's 16 miles an hour, and it's loud, as heavy traffic. Glass windows may shatter, okay? So at 200 miles, that's not so bad. At 50 miles, "16 seconds after impact, still a 7.0. Felt by all, many frightened, some heavy furniture moved around, a few instances of fallen plaster, damage is negligible. The ejecta arrives 2 minutes after the impact, and this can be up to a 3-inch piece of junk, with the average being a 1/2 inch. So think of the rocks that we just spread over here at TDS out on the road. 50 miles away, that's what's going to be landing. And that'll go on for a while, you know. This ejecta landing can last, you know, 1/2 an hour. Let's see, the air blast comes in, it's going to be 3.4 PSI. The wind velocity will be 115 miles an hour at 50 miles away. Wood frame buildings will be blown down, glass will shatter, windows will shatter, 30% of the trees will be blown down, some will have branches and leaves blown off, etc.
A mild hurricane.
Yeah, mild
Yeah,
hurricane.
Getting bad.
Yeah. And of course, if you're closer, you know, if you're 5 miles away, it's going to be a bad day. Because the crater's 4 miles wide, right? So this is fun. This is what got me intrigued, because not only do I like astronomy, but I like blowing stuff up.
Oh, that's right. You were a munitions expert in a submarine.
Actually, we carried 16 nuclear weapons on a submarine. So
Oh, I forgot about
you know,
that part. Yeah.
Yeah.
Let's just say it's a big thing that blows up.
Yeah. So you know, the fact that this is probably first, it was easy. It was an easy mission, not expensive in terms of what they wanted to do. I already had a couple of sample returns under our belt. This was our first one to go to an asteroid and try and do it. Definitely has a couple of these intervals here that are close in that same year, right? So impact probability, this is a very interesting. And Palermo scale, not really. Right now, we don't know that that's such a big number, but they have a complete listing of everything that we know about right now going out 100 years. And this has become, in a sense, the target list that we're interested in for future missions. And remember, this is observed anytime, let's see, probability. any impact probability. That raises it to 29. I don't want a Palermo scale. We'll set that to 0. Now let's set that higher. Let's go to 8.
What does Palermo scale represent?
It's a type of measurement of the chance that we're going to get smacked. There's Torino and there's Palermo, and they do, if you roll over it, it'll tell you. And you can go look these up in Wikipedia. So hazardous, when they rise above a 0, you know, that's when we get real interested. And we've only had, gosh, in the 18 years I've been playing ball, we've only had 2 of them that actually initially came out with fairly serious ratings. One of them I had some fun with. Let me see, is this it here? No, let me switch my screen one more time. So back in 2015, I had another asteroid come by on Halloween night called TB145. Okay, so let's talk about scary, okay? In 2015, 3 weeks before this flyby happened, this thing was discovered coming out of the sun, okay? For a long time, this thing's orbit relative to Earth put it in a position where we just didn't notice it, okay? It was Earth crossing, but it wasn't Earth crossing near Earth for going back 50 years. So asteroid studies really have only gotten going in the last 20 years, okay? And nobody knew about TB145 until 3 weeks before, and it was discovered, and suddenly this thing's coming really close to the Earth, okay? We're not absolutely certain when it was first discovered exactly where it was going, because it's coming out of the sun, and its deviation relative to us looking at it every night was like, hey, that thing's like coming straight at us, right? So they were able to capture a lot of data samples of it, but from what we could tell, we couldn't really predict its orbit perfectly. We just knew this thing's coming in. So on Halloween night, I set up my equipment, and this is what I got. This is exactly, let's see, I think this was from 12 a.m. I took 30 shots, I believe, and it was less than a half hour, and watch this thing go. It's going so fast, it looks like a Tic Tac. In fact, sometimes it's moving so fast, can help the Teletubbies thing. Again. Can you see that? Look how much area that covered in 30 minutes. That was crazy. And let's see, that was 12:12 to 12:24. It was 12 minutes.
And you could actually see it tumbling.
That wasn't tumbling. That was moving so fast that my camera in 10 seconds was de-integrating and splitting it. That's what I mean. You can de-integrate something that's moving fast. And it's not a dot anymore. And there's no way for me to track that on the object. It's moving so fast. It's like hold down your paddle and you're slewing at full slew rate. Well, not that fast. Photo rate with mine. So that was Halloween asteroid.
Wow.
So that was a lot of fun. And not only that, after I put this up, unknown to me, Phil Plait, the bad astronomer, how many of you know this guy? Heard of him? He still has his own thing going on. He wrote about it, and he got this one from a professional observatory. And that's the other style where they're guiding on it, but they had the software for it. I couldn't do it, right?
Yeah.
That's crazy. I love it. And look where the moon is. That was the other thing. The moon was right in the area that night at full. And then here's my crazy one again here on Slate. So even if you don't submit the stuff, you can still have some fun and fame. just putting up a good one. And he wrote about this. He says, you removed the streaking and the glare. Yeah, I did. I got rid of it. So one more time.
That is pretty cool.
Jerry, the fact that it's moving across the screen and has a fairly high rate, doesn't that kind of indicate that it's really not going to hit the Earth? And I suppose it didn't.
No, it didn't. Well, no, it didn't hit, and it wasn't going to. But we didn't really understand, until 3 days before it arrived, that it was going to miss us. For 2 weeks and 2 days, we were sitting here going, nobody was writing about it.
Yeah.
In the
If it's gonna hit
community,
you, it's going to be fairly, I mean, it's coming right at you. So
yeah,
its rate will be fairly low.
yeah, and it'll be 100 years before it does this trick again. Because it's the way it orbits and where Earth is at, it's not captured in our orbit. It's a crosser, right? I believe, let me tell you which one it is, just a second. That one is a ATIN. Earth crossing NEA with a semi-major axis smaller than the Earth's, and it's just a very narrow little bird in terms of its orbit. Let me show you. See this guy here? That's what it did exactly. Now, it kind of stays in that position without following along. It's not captured by us. So as we move around, we don't see it if it's over here and we're here, and we don't see it if we're over here and it's on that side. And that goes on for 50 years. That's pretty much its pattern. And then one day we get in the perfect intersecting position as it comes around, and you get a video instead of an impact.
Yeah.
So what's the protocol? I'm sorry.
Sorry, no, go ahead.
So what's the protocol? So you found it, it's aimed right for us, you've got data. What's the protocol? Who gets notified when and what order?
All right, so the first thing you do is you submit to NPC, and believe me, the instant that they see something that's brand new, that gets huge attention, and it goes out in the impact in the next 4 hours. So then we go to everybody in this, there's, like I said, 400 to 600 potential observers a night. And weather's a factor. Are they working that night for the pros? Are the amateurs interested in doing this? There's some very serious amateurs, Brian Warner being one of them, okay, right up here in the Riverside area. So the group that I have been playing with is, one's in London, that's North Holt Branch Observatory. One's in India, that's CFID Observatory. And then a couple of amateurs, one in South Africa and one in Australia. And we try to do handoffs to one another. And so if we get something hot, let's say it's me and I get lucky, and I find that, I report it to Minor Planet Center as soon as possible. Okay, like as soon as I pick it up. And there are ways to take something you pick up like that, and check to see if it's known at the Minor Planet Center. And typically, something that looks like an asteroid that's coming at you like an ATIN has to be discovered either early morning or just after sunset. You have to be looking where the sun's at, right? Either in the morning or the evening, within an hour or two of sunset. As soon as you can possibly be looking in that zone, you're looking for something that is coming in that particular orbit style, right? So if you pick it up then, Earth will likely turn away from it before you may pick it back up in the morning, okay? You may get lucky. No, you won't. You can only pick it up either morning or evening. I'm wrong about that. That's just the same thing as Mercury or Venus. But you picked it up, so now you're reporting. The next, in other parts of the Earth, at the same kind of relative time that you picked it up, relative to sunset, others can be in position to try and pick it up as well. Now, the trick is, if they pick it up and there's not a lot of change in the RA deck, that's very alarming. Anything coming from the sun that's new, that does not have a major change in RA deck, that's the moment when everybody goes ballistic. Okay, so now NEOWISE turns and Hubble turns, and every other instrument that we can get at NASA to take a look turns and starts producing data right away. Within 48 hours, you'll start seeing the impact coming out on something like that. Every hour there will be information just on that target, and it will become basically a very high value target in a sense, because you probably only have a few weeks if that happens. And ATINs are the ones that we're most worried about more than anything else. The ATIRAs, they are concerning, but they don't cross necessarily. Now they can cross if for some reason a resonance in the orbit causes a disturbance and forces it to change its orbit due to some resonance that we're not aware of, okay? And also another thing that can happen is capture. Something that wasn't necessarily an ATIN before, it was an amateur, and it gets captured in some weird resonance with the Earth, can get pulled into an ATIN type of orbit, but it has to be dramatic. There has to be something really weird about the moment when that resonance in the orbits changes and changes its path. But it happens. Because we're talking about rocks that, 400 or 500 meters, a kilometer, they're not that big, and we are big, and the moon's big, and all the other rocks are big. Mars and Venus and Mercury are even big, and they can all have an impact. And getting hit by a particular CME from the sun can have an impact, right? So when you have a coronal mass ejector, and that thing is in this portion of the orbit here, it gets as close to the sun as it does, and it's hit by a full-on CME, that can change its orbit. It's a playground. So, with all that being said, these pages at CNEOS are a great place to learn. And the last thing I want to get, preparations. Let's run over this real quick. Okay. First thing you want to do before you actually go try to record any asteroid is you have to set a precise UTC time for your FITS image, okay? Does everybody see that? So you need to go in and get your clock on whatever storage, or like for your cameras. Some of these new cameras are actually creating information with a clock built on the camera. The larger CCD instruments have that built in. The smaller ones just push the image to your computer. And when they do, you're going to want to capture that data. But if your camera has a built-in clock and it writes the FITS header, then you're going to want to sync that clock if you have that in your camera. The next thing you want to do is on your desktop, set it up with nist.gov, and before every imaging run, it may be 4 or 5 times a night. If you're doing different targets, before every target, sync the clock. It's incredibly important for astrometry. Know your limiting magnitude. Look for rocks that fit within it. Determine your arc seconds per pixel. It's super important if you're going to do astrometry or even photometry to be at 1 arc second per pixel, okay? Take darks and blacks. We're not going to get all up in the air about calibration, but it's useful, obviously, for getting the image into a condition that it can be processed. Prior to the data run, move to your expected location of the target and take a series of 3 images at 10, 20, 30, 45, and 60 seconds. Doesn't matter if the target is in there or not, but it's not a bad idea to do a series of 3 of each of these on the target so you can get a feel for whether or not you're making tic-tacs or nice round objects, okay? Look at those images before you start your real run. Make sure that you're capturing it, that it's in a sweet spot, that you're not getting some, globe noise or anything like that at the start of it, open up one of the images and verify your FITS header contains accurate data from that for each run that you do on the first, when you're doing these the tests. Just pull it into, if you don't know how to you can get FITS. The NASA has a FITS viewer that you can open up with, and then you can examine the table to see what information is being written. You definitely want the mount data in there with your RA and deck information being written. You definitely want whatever camera data can be written in to that FITS header. You want time information to be accurate and showing up in the FITS header. As much data as possible should be in that header. Down the road, you may end up submitting that if there's something really special that you pick up. And finally,
Jerry, what's the point in waiting 2 hours between these observations?
I'm sorry, say again.
Why wait 2 hours? Why not just when you finish the first run, do the next
Oh,
one?
you can do that, but basically the Minor Planet Center, when they're asking for astrometric data, it's going to want to see 3 samples a night and 3 quadrants in the sky, right? So if I'm going to do astrometric data, I got to do it for a couple of nights in a row on NEOs, and 2 nights in a row. There's a whole section on NPC about how to do this. I'll show it to you in a minute. But generally, what we do is we set up a series of runs on 5 targets in a 2-hour period. And we just go 1, 2, 3, 4, 5, and then come back after 2 hours. We've split that up. I usually do 5 a night. I have 5 targets picked out, and I wait 2 hours. And then when that 2-hour period, when I say wait, that's if you're only doing 1, okay? But yeah, there should be a delay between them so that you get it in different parts of the sky, because what happens is you're getting these with background stars, right? If your field of view is an arc minute or 2, and you wait a couple of hours, it's going to be in a new quadrant with new stars. When we start to measure the location of that thing, we don't want it to be so close to the previous location that we don't get an opportunity to work out the error in the astrometry, right? Does it make sense?
Yeah.
We're measuring against position of background stars.
Right, and the further apart your measurements are, the better the ephemeris you're going to get.
Exactly. That's the goal. All right. And then ease into it. Start out with main belt asteroids, less than 15th magnitude, and practice every step of the prep list repeatedly, like a doctor, from top to bottom. After 10 successful nights of hitting and that 10 nights ain't going to happen in a row. That's going to take 3 months, okay? But after you've gotten 10 perfect nights hitting every aspect of your prep list, you're ready for near-Earth objects. That's the next level. Now, you don't have to do this. You can do it any way you want. It took me 18 years to figure it out. So I'm recommending that this is not like, the work that you do with imaging for and PixInsight. This is radically different in its own way, okay? And you have to start planning months in advance to even get 5 targets a night into your plan. And when you do these things, you're going to be looking like 3 months ahead with NEOs, and you're going to try to make a nightly plan for 14 nights in a row around that NEO, okay, if possible even. So what you're doing is you're setting yourself up for early reacquisition. If you're doing 14 nights, that's 2 weeks. So what you're trying to do is early in the game is to reacquire something that's coming back around. So on night 1 and 2 and 3 and 4, you're just hoping to pick up a dot that gets brighter coming from the direction of Mars, right? Now, if it starts to get brighter and you're on it and you get some bad weather, you're going to have a few nights of bad weather, then you come back to it again. It might be now actually not just a bright dot, but moving. And so the weather, the moon's position, your rise, transit, and set time, sky position, All of these factor into your selection process. And believe me, trying to find a rock is that you can take a shot of ahead of time for NEOs. You can spend 5 hours a night and not find one good rock 3 or 6 months from now. Okay. Based on your imaging train, based on your limiting magnitude, based upon where you're shooting from, based upon the position of the moon, based upon how bright it is relative to, how much is it brighten up in the quadrant where you're shooting, how dim is the object. I mean, every one of these runs, like right now, my runs, I'm planning for July right now, and it's May. I may get some work in at the end of June, and I might even get lucky and have some stuff in 2 weeks I can shoot. But right now, none of it's good. So I have to keep looking ahead and waiting, and planning, and laying out a plan. But sometimes, if you really take your time, it takes hours and hours and hours and hours to do a night's run. And then after that, you can set that up. And once your plan is ready, just wait for the calendar to bring you into process. If you get lucky and you have a fun rock that makes the news and you manage to get a copy of it, you could get somebody to write about it. Have a little bit of fun with your movies. You don't even have to do astrometry, just do that. And let's see. Join the Rocks group. We have a groups.io, SDAA Rocks. There's the link. We talk about the stuff there. It's been quiet. I'm hopeful to grow a group of hardcore asteroid hunters here at SDAA. And I will share all these links and information. In fact, I'll get the PowerPoint in a PDF format, and we'll publish it on the AISIG group. And but I'd love to have you join. And anytime you want to come out here to TDS, park your car next to my observatory and set your stuff up outside and hunt asteroids with me. I'd be happy to do that with you. And I'll make dinner for you before it gets dark.
Woohoo!
All right. That's my offer. I'd love to have a bunch of people get on board and we could have some real fun.
Yeah.
That was super.
Does anybody have
Questions?
anybody got any questions that Jerry didn't answer?
Was that too much overload? TMI?
Well, I got to say, we started out with 19 people.
Yeah.
And one guy, somebody dropped off. We're down to 18. So
Wow.
we didn't lose any audience. So
Okay. And nobody told me I was wrong about anything. That scares me. What's going on out there?
Well, Jerry, I don't think you put them to sleep.
Okay, good.
I have a question that
Yeah.
for Jerry.
Yeah.
This is Jerry. So I'm kind of into photometry, right? So
Yeah.
this sounds a bit like photometry on steroids. Is there a, for those people who might be considering stepping into this, is there a quick and easy way to kind of get into it without like getting so far down in the weeds that you might be put off by the complexity of it all?
Well, photometry, Gary, I'm familiar with what you do out there, and you're awesome, especially when you're doing the star parties with Dave. And he told me you're an advanced, kind of accelerated astronomer around this stuff. So for you, it's not going to be hard. If you're going to get started in photometry, I'm going to teach that as a third class if I'm invited back. Okay. It's not that difficult. Basically, all of the fundamentals of photometry have to be observed as if you were doing any object, no matter what it is, right? Once you have, I would say, start doing photometry with stars. Get good at it there. And then ease into not necessarily NEOs, but the main belt asteroids again, because you need to get some time under your belt with easy targets. And then finally, jump into it with the NEOs. They all rotate, including the main belt. So, from my perspective, any of that is good. Let me see here just a second. I know the Minor Planet Center now operates let me look this up. I had it the other day, and I might still have a link for it. Where's my bookmarks? I hid them like a silly boy. There we go. And then under, no, it's not it. Asteroids, no, wrong one. Asteroids. Where is that? PDS, MP, I think it's the MPC. Oh, no, there it is right there. Shoot. Light Curve Gallery, Minor Planet Center, Photometry. Okay. Can you all see that?
Yep.
Okay, so this is the place with light curves that are published by the Minor Planet Bulletin. And then there's information about observers. And of course, this is nice because you've got emails, so you can talk to people that are doing this. Add observations, light curve gallery, that's all there. Presentation. Spanish amateur astronomers are collecting this under the cognizance of the Minor Planet Center. So I don't think they give good data on it. I do know this. There is a page at the Minor Planet Center. Shoot. Yeah, there it is. And let's see here. He has a link that goes straight to it. Let me look and see. Astrometrica is a good tool. Do you use that, Gary?
I use AIJ.
Okay. Yeah, that's perfect then. Where is the information on? I just saw the link.
And I'll definitely come out and take you up on that offer for dinner there.
Oh, that'll be fun. I would love to watch you do some work. There it is. Here we go. So this is on astrometry, and this gets you, oh shoot, they removed it. It's somewhere else. Oh no, Mr. Bill, the Center for Astrophysics. And they are part of this as well. So that's an old link. I am pretty sure if we just go to the Minor Planet Center itself, and we look for observers, publications, archiving of services. There we go. MPC submission info. There we go. Guide to astrometry. This is everything about astrometry. There we go. I'm interested in photometry. A good guide to minor planet photometry is available from Brian Warner. Brian Warner wrote an incredible book on this subject. I recommend it highly. Let's go see if it's on Amazon still. I bought that years ago, and that guy is the shiznit of photometry. And he's here. He used to be in Colorado, and now I think he's out here. Let's see. There it is. A practical guide for light curve photometry and analysis. That is the best book ever written on the subject.
Okay, cool. Thanks. Appreciate that.
That's my 2 cents. It's not cheap.
No, $50.
Yeah, but there's always a good chance you can pick it up secondhand. I get a lot of these books secondhand. You get them a lot cheaper.
Yeah, absolutely. So, but that is I bought that years ago when I was first getting into it. And before, so when, this is interesting, Scott, when I was I lived out here for 3 months at my observatory building that friggin' nightmare down there that became the Barrow. It's okay now, but back when I was
Yeah,
out
it's
here,
working. It's
yeah,
working.
that's when Potrero decided to catch on fire. And it was hot, hot, hot every single day. And Pat says to me, "What do you know about photometry?" And I'm going, "Well, I'm not going to tell him I don't know squat, but I had been, interested in the asteroid thing for a while. And I knew Brian Warner because that's his gig. I mean, if you look at the SAS conferences and what he submits, that guy's a machine when it comes to asteroids. And that's when I noticed he was doing light curves with asteroids. And so I said, well, I'll get back to you on it. And I bought this book. And then I talked to Brian about it at one of the SAS things. And everybody was saying, this is the guy. And it's clean, simple, it's clear. There's no confusion. It's orderly in the step-by-step process. It explains some of the hardest things to do with photometry, like calibration, in a way that's fundamentally simple. So to me, it's worth it. I mean, you couldn't pay him to come down and spend an hour teaching it to you. So $50.
Cool.
Anywho's, there's that. Let me stop now. Okay. Other questions? I got nothing else.
So Jerry, this is Carl Weber calling.
Hi.
You showed me one of your videos before and you inspired me. So I was going to show you one I took because of you.
Oh, awesome. Let's see it.
All right. Let's see if I get the sharing thing going here. Oh, of course, now I can't get this thing going.
Well, you have time. Don't worry.
Okay, are you seeing that?
I see I don't
we
see
see
anything but a white screen right now.
Yeah, we see a white screen.
Huh, okay, it says I'm screen sharing.
Hold on just a second.
Yeah, it's green and it says I'm screen sharing, so.
Okay, we'll stop.
Jerry,
yeah.
you unshared, right?
Yeah, I'm not doing anything right now. It's just
Yeah,
my
I've got
fat face. That's it.
Okay, well, never mind then.
Oh, no, maybe it's possible to do it again. Try to share again, but this time find the app. Don't click on that first one at the top. You might have been, it looked to me like you had selected the white screen share board.
Oh, well,
Yeah, try to.
Well, it's not important. But
I want to see it.
Yeah, I've been looking forward to seeing you so I can show it to you.
Yeah, I've been gone for a few years. I'm back permanently now. I'm not ever going to leave again.
All right, well, I'll have to show it to you some other time. Dang, that's too bad.
Oh, well.
Okay.
Okay. I was looking forward to that too. Okay.
Well, then try it anyway. Go try share again. Click on share screen.
That's all right. It's not that important.
All right. Is it on YouTube?
Actually, yeah.
Well, hey, I can share YouTube and find it. Hang on. Let's do that. Okay. YouTube. Entertainment, YouTube.
So
okay,
NEO Asteroid 1998 CR2.
Perfect.
1998.
Oh, what? Let me fix that.
Okay.
Which one?
Well, it's got my name on it, so just start scrolling, I guess.
Oh, well, let's put your name in there.
Okay. Oh yeah, sure. See his name in there now. It was there just a few minutes ago.
Well, you know what? I'm going to get rid of the CR2 part for a second. Control X and just search on Carl Weber.
I have a whole 2 videos there.
There's no
More than
channel.
one Carl Weber.
Oh, look at
Yeah,
that.
there is.
All right,
Control
never
B.
mind that. That's okay.
Oh man, I'm not done yet. We got nothing else to do tonight. It's quiet
Carl-
out here.
Carl, if you find a link to it, just send the link to
Yeah.
the AISIG group and we'll all take a look at it.
That's okay. Wasn't important. I just wanted to show Jerry.
Yeah.
Yeah, well, I'll hunt that thing down after this ends anyway and see if I can find it. That's pretty, I'm sure it's here somewhere. Oh, I know there's one more trick we can do. Control F, CARL. Hey, there it
There it
is.
is.
Found it.
Yeah.
Found it. Awesome. 16 seconds. Let's see this bad boy.
It's right in the center.
Oh, wow. In April last year. Look at that.
So that was my first try at ever doing that. Now it's after speaking to you.
That is friggin' awesome. That's beautiful.
Yeah, so that was my one and done.
Cool.
Well, that's the game, you know. You try it, you might like it, you don't like it. There's other things to do in astronomy. That's for darn sure. Lots and
Yeah.
lots of different things. I mean, Scott does exoplanets, so that's a
Yep.
whole nother interesting world of photometry.
Yeah, we haven't talked about that this year. Maybe next year we'll talk about it.
Right. Okay. So Scott, my deal would be if we wanted to do the astrometry as a class next, you know, I'm happy to do that, but you can go ahead and survey the crowd and see if they'd like to do that.
Yeah,
There's some tools. It may not be of interest. I know that I'm going to do these things separately through the SDAA rocks thing. And I also do these through NASA as well. Because there's that whole program I'm in, I always have trainings about every other month. So
yeah. Well, we've got time to do it, and I think if we do it in this format or in this in these meetings, then we ought to be sure that a substantial fraction of the normal
Yeah.
participants are interested in seeing it. So
Yeah.
I'll do a little research on that, and then we've got time September, October, November, and maybe you can do 1 or 2 of those months.
yeah,
So-
and if it doesn't work out for the AISIG group, I understand completely. This is not that kind of stuff. So we can do it. I'm actually setting
Well,
up.
I really think the photometry part, one of your other ones is aimed at photometry, right?
Right, that's the last step. Doing it, you have to get the. Well, you don't have to do the MPC submission, but I could do the photometry class instead.
Yeah, but the
Yeah.
photometry should be of interest, I think, to the imaging people, and
Okay.
it might be combined with a little bit on exoplanets or whatever. So
Right.
maybe we can figure out a way to put it together. So
For all of you still there, I really appreciate you attending tonight, and I hope to see you out here at TDS over the next few years.
It was a good
Well-
presentation. Thank you.
yeah, it was
Very good
great,
Thank you,
Jerry.
Jerry.
Yeah,
Thank
yeah,
you very much.
very, very interesting. So, okay, I guess that's it for tonight, guys. So thanks for coming, and we'll see you again next month.
Yeah, thank you.
Ah.
Bye-bye.
Bye-bye.
Bye.
Bye.